নমস্কার, শুভ সন্ধ্যা সকলকে। ওয়েলকাম টু টুডেস পডকাস্ট ইভেন্ট, Cosmic Codex by Cosmic Charade. We are thrilled to have you all space fans, astronomy enthusiasts with us as we embark on a journey through the wonders of the universe, exploring the latest discoveries and advancements in astrophysics and cosmology. My name is Samrit Pramanik, and I am honored to be your host today. By profession, I am a data scientist, statistician, and R programmer working at a private firm. But that is not my only identity. I am an astrophile, deeply passionate about stars, galaxies, nebula, and the cosmic wonders of the universe. Since childhood, I have been captivated by the allure of the night sky, pondering the vastness of and the beauty of the cosmos. The sheer magnitude of these cosmic wonders has always evoked a sense of awe within me, making me realize that how small we are in comparison. In moments of celestial contemplation, I find solace understanding the insignificance of human grudges, brutality, and violence in the grand design of the cosmos. This profound realization has kindled a deep passion within me for astronomy and cosmology. So during the lockdown in 2020, I, along with one of my brother, embarked on a journey by creating Bishoykar Brahmando, an Instagram page where we used to share notes on astronomical events, objects, and some astronomical facts on this. To expand this platform globally, beyond the Bengali language, we established Cosmic Charades in 2021. So initially, it was a simple LinkedIn page. We focused on writing blogs on various scientific disciplines such as physics, mathematics, chemistry, biology, statistics, computer science, technology, whatever, anything related to science. However, our vision was broader, aiming to create a bigger impact. So let me quickly walk you through our official website because at the in the year of 2023 we have launched our official website, so where you can find every detailed information about cosmic charades. So let me share that screen. Is it visible now? I
Yes,
think it is
Samrit, it
visible,
is
right?
visible. It is visible.
Yeah. Yes. So this is our Cosmic Charade official website, and here this is the landing page, right? And here, if you see, there is an about us section. Here we have the main, our objective, what we do, all is there. And here is the blog section. You can find total 29 blogs that has been published till to date. So here you can see that lots of topics we have covered like art, astronomy, astrophysics, Bayesian, conjecture, information theory, mathematics, music, networking, paradox, physics, probability, statistics, and technology. And there is another section, cosmic literature. So this section we are still not yet uh, explored. So we are still exploring this, and we are still, we are, we are to see something new in this section. And there is another section that is cosmic courses. So currently we are running one course that is computational thinking with R and Python. So this course is about to end this month. So we hope to start another batch in the coming months. We will let you know. So stay tuned, and we will get back to you. If anyone is interested, you can just ask in the group, or you can ask me directly. And there is the interesting section that is magazine space. So what is magazine space? So magazine space is, we have published one magazine, our first ever magazine, in the Kolkata Book Fair, the last Kolkata Book Fair 2024. This magazine, Bishoykar Brahmando, and we have this esteemed author in the first issues. You can see all of the names here, and these are the contents. So the physical copy is still available in the Dhanbindu Prakashani at College Street, and address of this store, the bookstore is this Bankim Chatterjee Street at College Square. So if any one of you want to buy this magazine, you can go there and buy from them. So with this mission, okay, so another thing is that Cosmic Squad. So I am come to this Cosmic Squad. These are the entire team, our Cosmic Charade team. We named as Cosmic Squad. I will come to this point shortly. So let me quickly tell you something that with this mission in mind, the Cosmic Charade, the establishment of the Cosmic Charade, first of all, we have successfully published our Cosmic magazine. That is the first step of our journey that already happened in the year 2024, early in January. And we are now excited to announce another thing is that we will be publishing our second issue, the Sharadiya Shankha, during the upcoming Durga Puja in October. So uh, you all are requested to keep an eye on the updates, and hopefully you will get to know about the publication date soon. So next, I am coming to this Cosmic Squad. I am very fortunate to work uh, with a dedicated team of the individual who shares this passion. Allow me to introduce them to you quickly. So as I said, I am Samrit Pramanik, and we have Abhirup Moitra. He is a science blogger and content creator. He is dedicated researcher specializing in mathematical analysis, mathematical statistics, complex dynamics, and fractals, aiming to inspire and contribute to the science and technology. So over to you, Abhirup. Please say something about yourself and introduce yourself in this community.
Yeah. So I hope I am audible, right?
Yeah, yes, yes. Go ahead.
Yes. So thank you for such a warm introduction for me and to introduce our platform Cosmic Share in front of our audience. So let me speak something about Cosmic Shared and Cosmic Shards and my experience with Cosmic Shared with from 2022 to as of now. So Cosmic Shard started with the initiative of a young fellow named Nandalal Devnath. So he started his platform by the name of Bishmaikar Brahmand by the making Instagram weekly content on astronomy and some of the facts of cosmos. Then to popularize this platform uh, globally, Shomrit started a LinkedIn platform by the name of Cosmic Share. Then at the starting on 2022, I have joined the team with a passion of science blogging. Uh, uh, I have simply 1.5 years carry out my continuous blog writing to get a higher reach of our platform to popularize our name globally. Then with lots of ups and downs, we have carried out our journey from 2020 to now 2024, and that's how we have published our first ever magazine on Calcutta International Book Fair. So you can check out our website's magazine space. Uh, so with the blessings of our audience and followers as well as our advisory team, especially Shounak Bhattacharya sir, we are carrying out our platform. So myself Avirup, so I am a self-driven individual with a deep passions for understanding the universe. So my research interest, especially lies on the mathematical analysis, statistics, mainly the theoretical statistics and the mathematical statistics. I am recently doing my research intern from Vellore Institute of Technology, Amravati, with the mentorship of Shantanu Nandi. So I have started studying on conformal dynamics systems and holomorphic dynamics, fixed point iterations, self-similarity and fractions. So I aim to share my fundamental and advanced mathematical concept to inspire research and contribute to science and technology. So so Kashmir Sats is more than a name, so it's a symbol of our collective curiosity and our drive to unravel the mysteries of the universe. So we are a community of students, researchers, and enthusiasts who believe that learning is a never-ending, and every questions we ask takes up one step closer to understanding the cosmos. So, our mission at Cosmic Surge is to create a platform where ideas can flourish and knowledge can be shared freely. So we aim to bridge the gap between complex scientific concepts and the curious minds eager to grasp them. So through seminars, workshops, and podcasts, we are aiming to strive to make science accessible and engaging for everyone. So in a short span of time, we have built our own website ourselves, uh, and then we have published our magazines, um, with our by conducting the coursework on R for everyone, and the approaching towards computational thinking with R and Python. And I would uh, I am very thankful to Kazi Abu Roshan, who dedicatedly conducted his from his busiest schedule. He took his time and conducted the coursework. So we are also proud to introduce our first ever podcast series, Cosmic Codex, our inaugural episode. From the basic to black holes, a step to learn general relativity, features by Shounak Bhattacharya sir, who is an educator and renowned uh, for his work in training and placement in Southeast Asia. So, looking ahead with envision Cosmic Shade as a beacon for science enthusiasts across the globe. We inspire, we aspire to create a vibrant community where every member contributes to and benefits from our collective pool of knowledge. So we plan to expand our outreach, collaborate with more experts, and continue to inspire the next generation of scientists and thinkers. So I would like to extend my heartfelt gratitude to all the members of Cosmic Shards, our speakers, and our audience. So your support and enthusiasm drive us to keep pushing the boundaries of knowledge. So let us continue to explore, learn, and share for the universe in vast, and there is so much more to discover. So thank you, and let's embark on this cosmic journey together. So again, over to you, Shamrit. Thank you for this warm welcome to me, and uh, giving me a scope to uh, and giving me a platform to showcase my skills and everything. Thank you. Thank you so much.
Yeah, thank you, Virup. Thank you for your brief introduction. And next we have Kaji Abu Roshan. He completed his master's in physics with a focus on cosmology from Indian Association for the Cultivation of Science. He designed our course approaching towards the computational thinking with R and Python, and mentors students and research fellows in developing scientific computing skills. So Kaji, over to you. Could you mic on and
okay, so hi everyone. So I am Kazi Abu Roshan, and I like Samridha says, so I have clearly done my master's degree in physics, and it's focused on cosmology and high energy physics. So I have recently joined this group like few months ago, and I really love to teach things out, especially like cosmology and this computational fields. So, and I hope that you guys enjoy this particular podcast session and also our magazines and things like that. So okay, thank you.
Yeah, thank you, okay. Kaji. Thank you very much. Next is Shondipan Mondol. He is content creator and head of the Cosmic Art and Literature. He is undergrad in physics from Calcutta University. He had developed his interest in astrobiology, paleontology, astronomical art, and science fiction since childhood. So Sandipan, over to you.
হ্যাঁ, am I audible?
Yes.
হ্যাঁ, আমি তাহলে বাংলাতেই বলছি, ঠিক আছে?
হ্যাঁ বল অসুবিধা নেই।
হ্যাঁ হ্যাঁ, তো আমাদের এই কসমিক স্যারের জার্নিটা সেই 2020 সময় থেকে শুরু, যখন জাস্ট লকডাউনটা পেরিয়েছে। জাস্ট লকডাউনটা শেষ হয়েছে, তারপরেই আমার সমৃদ্ধার সাথে পরিচয় হয় এবং নন্দর সাথে পরিচয় হয়। তো প্রথমে তো কসমিক স্যার এটা শুরু করেছিল নন্দ, তারপরে সমৃদ্ধ এসে জয়েন করে এবং দেন আমি জয়েন করি। এবং আমার সাথে আবার ভালো বন্ধুত্ব ছিল সেই সময় অভিরূপের। তো আমার সাথে আবার অভিরূপ আমার ধীরে ধীরে আমার সাথে জয়েন করতে থাকে। এইভাবে আমাদের একটা স্কোয়াড তৈরি হয়, এবার আমাদের একটা টিম তৈরি হয়। এবার আমাদের টিমের সবচেয়ে যেটা ভালো বৈশিষ্ট্য সেটা হচ্ছে আমাদের টিমের এক একজনের এক একটা বিষয়ে ইন্টারেস্ট হয়েছে। যেমন অভিরূপ স্ট্যাটিস্টিক্সে খুব ইন্টারেস্ট হয়েছে, ও সমৃদ্ধার অ্যাস্ট্রোনমিতে ইন্টারেস্ট হয়েছে, অভিরূপের অ্যাজ ওয়েল অ্যাজ অ্যাস্ট্রোনমিতে ইন্টারেস্ট হয়েছে। আমার অ্যাস্ট্রোনমির সাথে কিছুটা অ্যাস্ট্রোবায়োলজিতে ইন্টারেস্ট হয়েছে। তো সমৃদ্ধার কথা মতোই আমরা প্রথম দিকে বেশ কিছু আহ, মানে এক্সপেরিমেন্টাল টপিক নিয়ে লেখালেখি শুরু করি, যেটা পাবলিশ হতে থাকে আমাদের ইনস্টাগ্রাম পেজে। তো সেখানে আমরা অ্যাস্ট্রোবায়োলজির উপর বেশ কিছু কন্টেন্টস লিখি। তারপরে আমাদের নিজস্ব কিছু মানে ব্যক্তিগত চাপের জন্য আমাদের লেখাটা বন্ধ হয়ে যায়। আবার আমরা ধীরে ধীরে কন্টেন্ট নিয়ে আসবো অ্যাস্ট্রোবায়োলজির ওপর। মূলত আমি অ্যাস্ট্রোবায়োলজি নিয়ে কাজ করছি। এবার সামনে দেখা যাক, সামনে আরো এক্সাইটিং বিভিন্ন জিনিস আমরা নিয়ে আসবো। থ্যাংক ইউ।
ইয়েস, অবশ্যই। থ্যাংক ইউ সন্দীপন, অনেক ভালো কথা বললি তুই আমাদের। And yeah, so next is Snigdha Bose. She is educational instructor and likes to think about stars, patterns, and anything on non-linear. Her curious mind is fond of playing with words, tune, chords, rhythm, curves, spices, and rooks within this curvature of space-time. So Snigdha, over to you.
আচ্ছা, গুড ইভিনিং সবাইকে। আমিও বাংলা ইংলিশ মিলিয়েই বলছি আজকে।
হ্যাঁ নিশ্চয়ই।
তো আমার কসমিক শ্যারাডে জয়েন করার হয়তো এখনো 2 মাসও হয়নি। আই জাস্ট কমপ্লিটেড মাই এমএসসি ইন দিস ইয়ার। তো অভিরূপ কসমিক শ্যারাডের পোস্ট দিত এবং গত বছর বিস্ময়কর ব্রহ্মাণ্ডর বিভিন্ন আমাকে কোথায় পোস্টেড পাঠিয়েছিল, সেখান থেকে কসমিক শ্যারাড সম্পর্কে আমার জানা। তারপরে আস্তে আস্তে গ্রুপ জয়েন করা এবং গ্রুপে জয়েন করে হঠাৎ করে কসমিক স্কোয়াডের সদস্য হয়ে যাবে। and I feel so much honored as you guys count me in your group. তারপরে আমাদের বিভিন্ন রকম কোর্স ডিজাইনের প্ল্যান হচ্ছে এবং সেটা নিয়ে হয়তো আমরা পরবর্তীকালে এগোবো। তার জন্য আর আজকে যে প্রোগ্রামটা রয়েছে তার জন্য আমরা আশা করছি আজকের প্রোগ্রামটাও খুব ভালো হবে। তো এটাই।
Okay, thank you Snigdha for your introduction. And finally we have Rajat Kanti Chatterjee. He is graduate in applied physics and passionate about astronomy, cosmology, and seeks to enhance his practical skills in dynamic workplace. So Rajat, over to you.
Good evening everyone. I am Rajat Kanti Chatterjee and it is a great pleasure to be here with you today. I have recently completed my MSc in physics from West Bengal State University, where I cultivated a deep passion for the mysterious of the universe, particularly in the realms of astronomy, cosmology, and condensed matter physics. Today, we embark on an exciting journey exploring the fantastic world of general relativity, from the understanding the fundamental principles to delving into the enigmatic phenomena of the black holes. Our session aims to unravel the complexities of this profound theory. I look forward to our discussions and the insights we will share as we traverse this captivating subject together. Hope you all enjoy our first podcast. Thank you.
Yes, thank you Rajat for your introduction. And finally we are now getting started to our main agenda. So today we are privileged to have a distinguished speaker with us. Please join us in welcoming Mr. Shounak Bhattacharya with his session titled From Basics to Black Holes, Steps to Learn General Relativity. So with more than 16 years of experience, Shounak sir is currently working in an international educational institute and taking care of the training, grooming, placement of more than 6,000 students across Southeast Asia, especially Thailand, Vietnam, Malaysia, Singapore, and some other parts of Central Europe. He is also a member of the Defense Committee for the East Bridge University, Paris, and guiding the students who are pursuing their PhD. So being a passionate teacher in the field of science, Shounak sir runs a YouTube channel, Physics for Students. He is also a professional translator of Arabic language, plays piano and writes poems, and also translating literature in English from Urdu and Persian languages. So welcome Shounak sir, Shounak Bhattacharya. So over to you, sir.
Okay, am I audible?
Yes, you're audible.
Okay. First
Please,
of all, thank you very much. Samrit, Avirup, Shondipon, Snigdha, Rajat Kanti, they're all are very young, I would say students. I would like to, thank Cosmic Charade for giving me this unique opportunity to speak on general theory of relativity, although I have conducted already around 6-7 independent webinars on my channel, Physics for Students. Samrit has been great in communicating with me. First of all, I came in contact with Abirup. Rather, Abirup came in contact because I think he is basically the oldest subscriber of my channel. And I really did not recognize one day Abirup when he told me how to make a dual summation of the arithmetic. Can you please tell me? I am really honored because this is a very young, set of people, Samrit and others who have actually doing a wonderful job. And I also published one of my writings on Gregory Perelman. I'm thankful for Cosmic Charade entire group for giving the opportunity to publish that essay in the last book fair. And Samrit has already given a deadline of August, I think, Samrit, that I have to submit a kind of a writing. And this time I'm working on something on the historical development of Einstein's general relativity. So it's great to be, and it's an honor to be with all of you and the audience who are there. So as I always tell that I don't know anything, I'm still a learner, and I would try to expand the horizon of general relativity as it comes so that you can get a better understanding in a different fashion. It won't be too much of a mathematics, but I will take you through a different way. So with that, it is already 8:30 and I have got a few important things to discuss also. I would request the permission of Samrit that can I start sharing the screen, Samrit?
Yes, sure.
Okay.
Let me stop sharing.
Yeah.
Yes. Please go ahead.
Just a second.
Yeah.
It's showing an error. Just a second. Samrit, can you just help me?
Yes. Your screen is shared already. You can just open your PowerPoint. Yes. Now
Is it visible?
I can see. Yes, it is visible.
but I cannot see. Wait.
Just click the hide. Now you can open the PowerPoint. Yes, we are now seeing your screen. Yes.
But in my screen, it is showing all small. Just a second. Okay,
Yes, now we can see.
Okay. Okay, so first
Okay,
of all,
excuse me,
yeah.
yeah, sir. I want to say something. So before going to start, I want to say one thing, that is, for this is for our audience, is that if you have any questions or anything you want to, so you just raise your hand, then we'll take your questions, and we'll uh, convey your question to sir, or you will have our Q&A session after these talks. Okay, so be ready with your questions, then we'll uh, get back to you. Okay, so thank you.
Okay, can anybody tell me that what currently you are watching on the screen, because I cannot see anything from my laptop. What can you see right now?
Right now, your PowerPoint is visible actually.
No, but the first screen, what is general relativity written, that can you see that?
Yes.
Yes.
Okay.
You
Okay.
just
So first thing is,
yes. You just full screen. Make this full screen. Yes.
Is this okay?
Yes. Just click on the hide as well, so that that bar will be hidden. Okay. Fine.
Is this fine now?
Okay.
It is actually showing the next slide, not that what is general relativity.
Yeah, I am coming to that. Right. So just to start with, November 1915, as you can see, these are some amazing results that on the 4th of November, that is a Thursday, on general relativity was published. Then again on Thursday, on the general theory of relativity, the addendum was published. Then on 18th, again, explanation of the perihelion motion, which was basically the correction of the perihelion precession of Mercury. This was established, and then the fields of equation of gravity, which is the last equation of gravity of Einstein's, that was published on another Thursday. So everything happened on Thursday, on November 1915. So this is something remarkable. So mark on your life also Thursday to be a very lucky date, because everything happened on a Thursday. Okay, so this is just to tell you in short that what is general relativity. It is a geometric theory of gravity. It was published in 1915, and what it does actually is that it refines the theory of Newton to a theory of gravity. Now, when I tell the word refines, that does not mean that it is wrong. I see a lot of young students telling that Newton was wrong, Einstein was right. It is not like that. It refined. That means it made a better improvement of Newton's theory. So the straight lines, they got generalized into geodesic, which is a typical concept of differential geometry. The time and space, which was thought to be different, time on the x direction, space on the time on the y direction and space on the x direction, they got together into what is called a space-time, where there is no different identity of what is a space or what is a time. And this led to some great extraordinary cosmological events to study, for example, white dwarf, black hole, neutron star, etc. I actually saw Sandipan, Snigdha, those who are already studying astrophysics. So possibly these are great ways of studying. And Einstein's general theory of relativity depends on one single equation, which is called Einstein field equation, which we're going to explore. And these resulted into a lot of tensor mathematics, which came into black hole, gravitational time dilation, gravitational waves, etc. Okay, just to interfere once more, that as because I cannot see anything except my big screen, so I would request Samrit or anybody, if you want to ask me something, rather than raising the hand, talk to me, because I am unable to see the audience. I'm just viewing my full screen. Okay.
Okay.
Right. And from
Sure, I
time
will.
to time, yeah, this is
Let you
my
know.
habit to ask you that, can you see? Can you see? So please do respond. Okay. Now you see,
Okay.
one thing you see, that whenever you talk of general theory of relativity, what you see is that there is a kind of a structure like this, and there's a heavy ball or a heavy mass which is right on the structure. That is a space-time curvature. And some people say that this is wrong, this is wrong. No, I would say nothing is wrong. These are all absolutely perfect. So what it tells, that there is a heavy object, it creates a kind of a dent, and this dent is on a grid which we are going to study. Now, why I am showing you this picture is because of this. Now, whenever you go to internet and type out what is general relativity, you come across page.com, Wikipedia, Britannica, all those websites. Now, the point that I'm trying to make is that whenever you type general relativity, and what you get is a geometric theory, is a theory of geometry. It is something which is space-time tells matter how to move, matter tells space-time how to curve. So it is all about geometry and more of the curvature, etc. So that is the essence that you get from general relativity when you type it over internet. So from here, what we come to know is that it is a study on the curvature of space-time, which is caused by the presence of mass and energy. Now, this study, when I say that it is a study on the curvature of space-time, this actually calls for a shift in terms of your thinking, mathematics, your study, everything. I'll just pause, and I will like to talk to you for a few seconds. I will go back to my slide again. The reason is that what I'm trying to tell is that this shift from the usual mathematics, usual notion of Newtonian mechanics, or classical physics, I should say classical physics, this has got a remarkable effect in terms of our understanding, in terms of your understanding, in terms of the mathematics. So when people say, oh, general relativity is very difficult, no, it is not difficult, first of all. It is a shift in terms of a mental thinking. Now, if I tell you tomorrow that instead of waking up tomorrow in the morning, you wake up at night, and then you wash your teeth, and then you go to your washroom and start your daily work at 2 o'clock at night, you will feel that what Shounak sir is telling, he's mad or what. So the basic idea is that this is a mental shift, and I'm going to show you what is that shift so that you can understand. Okay, till now, is it all clear? You can view the screen and everything all okay? Everything fine?
Yes, your screen is fine.
Okay, so this is one thing which you need to understand. It is a geometric understanding of space-time. Now you see here what happens when you are learning special theory of relativity. What are you learning? You're learning about speed, velocity, frames of reference, etc., isn't it? So that means special theory of relativity is something which is related to speed, time, and space. It is a relativity. It is a study of simultaneity. On the right-hand side, when we talk about general theory of relativity, what you see, it is a study of geometry, curvature, non-inertial frames, curvature, surfaces, etc. So the shift that you have in your mind, remember, is that you are not going to learn too much about relativity. You are going to learn more about geometry. And that is why I say that it is not a general theory of relativity, it is a general theory of geometry. And the reason is this, that you will not learn much about what you call length contraction, time dilation, etc. You will learn more about geometry and how does geometry affects the study of the space-time. So this is my name, don't take me wrong, general theory of geometry. Okay, so as I told you that whenever students take up general relativity, there is a shift and there is a fear that, oh my goodness, this is going to be very difficult, tensor calculus, curvature. No, so you need to have a mental preparation. And the mental preparation is this: you need to have a very good visualization. You need to have a good abstract reasoning, because all those concepts will now become very abstract. you need to go through a very good logical understanding, and there will be geometric transformation, because remember, those Euclidean spaces will no longer work. What is going to happen is that you are going to transfer that geometry into a non-Euclidean curve geometry. So I remember, I don't know whether you have heard this person's name, Neil Turok. Neil Turok. You go to YouTube and search out. Let me just a second. Neil Turok.
Sir,
Yeah,
is
Neil
he,
Turok.
sir, is he was the director of Parameter Institute?
Perimeter Institute. You're absolutely right.
Yeah.
So Neil Turok, actually one of his lectures told that what is difficult, general relativity or quantum mechanics. So Neil Turok told that quantum mechanics is mathematical and general relativity is intuitive. That means, try to understand, I mean to say, those who are listening to me, that if I close my eyes, say for example, all of you, I would say, close your eyes. Okay, I close my eyes. And I say, okay, here is a cube. Okay, let me imagine what is a cube. And then you break the cube in two pieces. Okay, I break the cube in two pieces. Then I twist the second part of the cube in this direction. So what is happening? What is happening is that you are thinking in a very abstract way. Are you getting my point? I mean to say, Bhaskar, Ankush, Priyanshu, all of you are listening. So whenever you are closing your eyes and you're trying to think something abstract, that is requiring a visualization power. Quantum mechanics is very mathematical, isn't it? The eigenvalues, the eigenfunctions, all the vector spaces, these can be dealt mathematically. So if you're very good in mathematics, go ahead and make a career in quantum mechanics. But if you're very good in visualization of abstract concepts, then you should go ahead and make a career in general relativity. So that is why I say it is more intuitive than mathematical. Okay, now what I would like to tell is this one, that remember, general theory of relativity is again a very classical system. Now hold on, what do I mean by classical system? Do I mean Isaac Newton, Galileo, Kepler? No. I am trying to explain something very deep. And this lecture, I would recommend the book of Professor Leonard Susskind. You should go ahead and watch that lecture in order to understand the basic difference between a classical system and a relativistic system. Or I would say classical system and a quantum system. Today's discussion is related to relativity, so I won't speak about quantum system. I would speak about classical system. What does it mean? You need to understand that so that you can really go deep into the philosophy of classical physics. I'm again not talking of mathematics, even deeper, the classical philosophy of classical physics, so that you can understand that why general relativity is considered classical. Now, here you can see that if I take a dice, okay, a coin, which has got a head and a tail, then what I can do is that in a classical system with no discrete jumps, a head will go into a tail would come into a head. Okay, and if I take a coin which has only a head, which Amitabh Bachchan showed in Sholay, which has only got a head, so if I toss that Sholay wala coin, then it will only come to head and tail. And if I toss that coin which has only got a tail, Amitabh Bachchan is only going to win always, and it is going to be tail, and tail. So what I'm trying to mention is that a classical system evolves in this way, and if there is a passage of time, then it is called a dynamical system. Any system which is evolving with time is a dynamical system. Clear till now? Okay. Now here you see, this is something interesting. Suppose from point number 1, I go to point number 2, and from point number 2, I go to point number 3. Again, from point number 3, I come back to point number 2. This is fine. That means a dynamical system is reversible. I can go, I can come back. Now, suppose the second scenario where this man is standing at point number 2. And I ask that, for example, Abhirup is standing over there. Okay, I can always, take the name of Abhirup. He's just like my son. So Abhirup is standing at point number 2, and I ask Abhirup that, Abhirup, where are you just before at point number 2? Now, Abhirup cannot tell me that. He is just at point number 2. He has got no past, but he has got a future. He can go from point number 2 to point number 3, and from point number 3, he can come back to point number 2. So this is what is called a spontaneous system. In quantum mechanics, you all know it is called a spontaneous emission. So if a system is something which has got no past, this system is called an irreversible system. And that is not a classical system. Am I clear? Can somebody tell me yes or no? Or I am not talking nonsense?
Yes, sir.
Are you getting my point? Okay.
Yes, sir. It is clear.
Right.
I can
Right.
visualize
I want
that.
other speakers. I want other speakers also to talk.
Yes.
Because
Yes.
Abhirup has already. Yeah. So from state number 1 has no past because this system is irreversible. So if a system is irreversible, that means if I don't know my past, then it is not a classical system. And remember, quantum systems are not reversible system. If I take a kind of an atom and it suddenly emits a kind of an electron, then I have no way to tell whether that electron will come back and land onto that particular nucleus because the energy might have been lost. And there are infinite amount of possibilities for that subatomic particle to dissipate. So this is very much clear into this book. As I told you, this is how to learn general relativity. So please go ahead and check this book, The Theoretical Minimum, and check on the chapter number 1, The Nature of Classical Physics, which will give you a clearer idea. So general relativity is very much a classical physics because it can tell what is the past, what was the past, and what is going to be the future. Okay. The first thing that you need to learn, I mean to say, if I come to teaching, learning general relativity, is calculus. And the reason you can see is that a lot of equations in general relativity, the geodesic equation, the Schwarzschild metric, all these are coming from partial differential equation. And Einstein field equation also are a set of, I will come to that, what it is. So question is that why you need to learn calculus to understand general relativity? This is the answer. That Einstein field equation, which is a set of 16 equations reduced to 10 ordinary, I would say nonlinear partial differential equation. Even you can see the gravitational potential and then the derivation of the metric tensor. All this requires a thorough understanding of calculus. Now this is actually one of my derivation which I did on deriving what is a metric tensor. I just wanted to show you, you see these are all partial derivatives. And if you want to really see what this video is all about, then what you can see is this one. This is basically the derivation of the metric tensor, the line element. And if you want to know more, I will just pass on, hold on the link to your chat box so that you can really understand that what is the derivation of metric tensor. I'm not explaining it right now. It's a very detailed video which you can check out later. I'm just giving this link to the chat box. Where is the chat box? Yeah. So this is the link which you can later check in, and this will give you a thorough understanding of what is the metric tensor.
Yeah, sir, we'll share this link in our group as well.
Right. Okay. So that is the reason that you need metric tensor because, the calculus, because everything is depending upon partial differential equation. Okay. Now, you might ask me a question, okay, tell me that what are the concepts? We understand that, Einstein field equations require partial differential equation, but can you show me, are you speaking sense, Shounak sir, or you're speaking nonsense? So what are the concepts of partial differential equations which relates to general relativity? So in this way, you can have a better understanding. So you see this linear and nonlinear partial differential equations. These things are very well defined. Elliptic, parabolic, and hyperbolic equations. These are also required because gravitational waves, etc., are described using this part. Existence and uniqueness theorem, stability and well-posedness. I'm not explaining this, but just to give you an idea that calculus is very much required. Okay, now I come to what are called the best books on calculus. Now, when I talk of best books, already you are all physics graduate, you know much better than me, but I'm just telling you what could be the easiest book. Suppose somebody does not know calculus and somebody knows calculus but wants to go much deeper into that. Now, I would recommend, this is an excellent book. I mean to say, I am thinking of making a complete course out of this book. It is called Thomas Calculus, and it contains everything. I mean to say, if you are an absolute beginner, say for example, class 10, you have no idea about what is calculus. you can pick up this book, 1000 pages and more. I tell that thick books are better than slim books, because thick books are better. Why? Because they assume you know nothing. So they will tell you what is a function, etc. And it has got excellent illustrations, etc. Thomas Calculus, Early Transcendentals. It is a very good book which you can go through. So here you can see this is the overall content, or there's a huge amount of content is there, functions, applications, integrals, derivatives, infinite sequence and series. It's a very good book you can go through. This is a book which is for absolute beginners who have no idea about calculus. But remember, this book does not contain much of partial differential equation. It just contains the basic ordinary ODEs and a step-by-step approach, but a super book by Sylvanus Thompson and Martin Gardner. I hope you know who is Sylvanus P. Thompson. And this is an excellent book. It is free, easily available at Project Gutenberg. I repeat the name. You go to internet and search out Project Gutenberg, Gutenberg, and you can download this book. It is free, copyright free. You can very well read this book. Okay, this is my father's favorite. I just thought to tell you, this is an old book by Mir Publishers, Moscow, Differential and Integral Calculus by N. Piskunov. Very rigorous, doesn't contain much about partial differential equation, but very good in differential and integral calculus. Now, you might have a question
This
that
is
do I need
also my favorite as well.
Okay.
I have both the
Okay,
volume.
great.
Yes.
You have got the volumes, okay. Yeah, Apurva, what is your question? Tell me.
Sir, I have a doubt. So,
Yes.
hello, am I audible?
Yes.
So you talked about a reversible and irreversible event or something like that?
Yes.
That if anything happens spontaneously. So
Right.
I'm remembering. So in this semester, it was my last semester in BSc Physics. So we were studying about Drude theory, which is considered a classical theory of electron gas, something like that. But there, the collisions was happening spontaneously.
Right.
Like we were assuming something like the collision, after the collision, what will be the future? It is completely independent of its past.
Absolutely.
So yeah, so but still they are saying that it is a classical theory. So I have doubt here that is it a classical theory?
No. I mean to say spontaneous emission. In case, for example, an electron spontaneously emits something. Now, if I want to trace that particle, and if I want to trace back that where it will ultimately come and land into, that is very difficult. But under certain very closed experimental system, we can even trace back. But when we are tracing back some amount of energy, some amount of momentum, these things will be lost. Because for quantum mechanics, what happens when it emits, it gets into infinite possibilities. And you really don't know which possibility will ultimately keep it backtracking. That is why the Feynman diagram actually helps you to learn those infinite possibilities, and it is called the path integral. So yes, you are right. It is a classical theory, definitely. But in case of a quantum physics, when the emission happens, you really don't know where it will ultimately land and come up to. So that is why the system is not reversible. Just the way you are throwing a ball on the wall and it is coming back, the pendulum is going back and forth. You know exactly the position and momentum, where it will go and where it will come, the pendulum oscillation. But in case of a quantum physics, the emission of an electron, etc., won't be able to get you back on the original. Even if you get it back, you will see some amount of energy and some amount of this stuff will be lost. Right, Apurva?
Yes, sir. But so my still my doubt is that so Drude theory, is it a classical theory or similar to this electron emission kind of?
Group theory is if you're talking of the mathematics of group
No,
theory.
sir, not group theory. It's Drude theory, electron gas theory, classical.
I think he is talking about Drude's model, which we learn in
Drude's model, yeah.
Oh, okay. Yeah,
Drude's
that
model,
is
yeah.
classical in nature, definitely.
But they say that the past is completely forgotten by the particle when the collision happens.
Yeah, because
so
that is what I am saying, that if suddenly something is emitted spontaneously, how can you trace back the past? The past is not there. That is the that is the basic definition of what is called spontaneous emission. Spontaneous means what? That I have not got the past. It is suddenly emitting. It is suddenly emitting. It is suddenly coming.
Yes, sir.
So if it is suddenly coming, where is the past? Now, if I am suddenly born today, where is my past? Who are my father, mother, etc.? I really don't know. So that is why the past is not defined.
So the Drude model should be considered as not classical.
Not classical.
But they are still saying that it's a classical model of solid.
No, that is a classical model because they're using the classical model to study the gas, etc. But I am talking of a spontaneous emission in terms of the quantum arena, where the electrons, etc., suddenly emitting, and you really don't have any hold of the path.
Okay.
I need to check.
Sir.
Yeah. Okay. And Ankush has a question, right? Ankush, do you have a question?
Yes, so it's not like a question, just a comment maybe to someone who was asking about this Drude theory. So I'm not very sure about the full because I have to look it up. But the thing is, the quantum thing that can come in is like after the collision of any two quantum objects, be it electrons, be it atoms, whatever. After say atom 1 and atom 2 collides and then they go into a new state after collision, it is difficult to say that after the collision which is what. It is not like a blue ball and a red ball that after collision comes out to be a blue and a red there.
Absolutely.
So this is called the indistinguishability of the atoms or the electrons or the microscopic quantum objects.
Absolutely.
So that may be one way to look at things, whether in the Drude model, as I said, I cannot recall it completely. It's never always possible to sort of remember everything in one go. But maybe that is what they are talking about, whether the indistinguishability of the atoms or electrons are taken care of or not. Maybe that is the way to look at things. I mean, just
just a
comment on that.
Yeah.
So
let me quickly go back because I have a lot of stuff to cover and the time is limited. So now my screen is visible. Is it visible?
Yes, sir.
Yes,
it's visible.
Okay, and this is also a good book. So if you want, you can contact me later. I will tell you the names of the book. So just to give you an idea that this is also a very good book on K. Sankara Rao's because it helps you to clear net, get and all other examination. This is another book which is on partial because we are talking about partial differential equation. Yehuda Pinchover is a great person, great mathematician. I don't know you know about Yehuda Pinchover or not. And this is again an introduction to partial differential equations, a very good book to learn. Peter Giolver's book, this is a little bit expensive, but it is very good for self-study, Introduction to Partial Differential Equations. This is the content of the book. Overall, you can see around 450 pages, but gives you a clear clarity of that. Now, this is important. Why we are learning partial differential equation? Because Einstein field equations are a set of 10 partial nonlinear differential equations. Because PDEs are used to express relationship between stress energy, etc. Because many solutions of PD Einstein field equation cannot be found analytically, because it involves 4 dimension and so on and so on, we come to the conclusion that hence we need to learn partial differential equation. So one part of our learning is clear. Pre-calculus by Tarasso. Yes, this is also good. Yeah. So one part we have cleared is that general relativity is its classical nature, and we need to learn partial differential equations. Why? Okay. Now this is one link which is nowadays are getting very popular thanks to all of you. How to learn the mathematics of general relativity? You can go through my channel Physics for Students. In this playlist, you will get a better idea about all those things. This is, I'm trying to summarize because the time is short. Okay. The next thing again which comes is that linear algebra. So what are the mathematics? If you talk of the mathematics, first PDEs, then linear algebra. Now why linear algebra? You can see that this metric tensor, stress energy tensor. On the other hand, you can see the usual linear algebra, the matrices, the components, etc. So in order to know what is the relationship, how the matrices are done, is linear algebra important to understand general relativity? Yes, you need to have a very good understanding of linear algebra. Now, here you see, again, the question is why. The reason is that this metric tensor, which is actually the inner product on the tangent space, and the Ricci tensor, which is a contraction of the Riemann curvature tensor. So when we are contracting, when we are diagonalizing, we are trying to find out the determinant of a matrix, everything depends on linear algebra. So linear algebra has to be a must. Okay, let me explain you quickly what is this. On the left hand side, what you see, this 4 by 4, this is what is the metric tensor. G00, G01, G02. These carries different meanings about how we will explain other day, because I have a, this is how to learn general relativity. And what is general relativity? I conduct a monthly program on general relativity separately on my channel, which you can all participate, it's free. So you see that common components gets cancelled out, 3-1 and 1-3 and 2-0, and these things get cancelled out. And what we get is that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these 10 components are the metric tensor. If you tell that, okay, what does metric tensor do? Just try to understand that metric tensor gives you, like a Euclidean space, what is the time, what is the distance, how you see these red dots. So from one point to another, it is better I would have a chalk on the board. Anyway, from one point to another point, what is the distance, what is the angle, how far it is. So the entire, what we call causal structure, you understand what is. The causal structure of space-time is captured by this metric tensor. And I have already derived that metric tensor, which you can watch it, I have given that. And it is a symmetric tensor. So the components of mu nu and nu mu can be swapped. Now, if you ask me what is the significance of a symmetric tensor, I will talk later. A lot of things happens. It also carries a relation with Noether's theorem, but that is too technical. I will, anyway, so we understand these are all based on linear algebra. Also, you can see that the stress energy momentum tensor, which involves all the material part of Einstein's field equation, is comes from linear algebra. So here are all the details: vectors, length of a vector, diagonalization, metric tensor, volume element. We will come to this, what we call volume element. All this comes from the determinant, etc. So these are all what is called coming from linear algebra. And these concepts are inherently related to linear algebra. So a very good understanding of linear algebra is required. Okay. Now you might
sorry to interrupt.
Yeah.
Sir, one question has come up in the chat box.
Okay, let me see. Oh, where is
Yeah.
the chat? Okay, sir, can we please get directly on the theory part of relativity? Yes, well, if you talk of the theory part of relativity, who is that? Let's evolve. Okay, we are mostly covering on the how part. So this particular today's podcast is mostly on how to learn general relativity. If you are looking at what is the theory, that means what is a metric tensor, what is stress energy momentum tensor, then this won't be the right platform, because then we have to make another podcast. We're speaking purely about the concepts of general relativity. Okay, but still there are certain theoretical part which I will definitely cover. Okay.
Sir,
So as you can see, yeah.
Sir, one thing I want to say that your battery is going to very low, so please connect your charger, otherwise you will disconnect and we'll lose you. Okay.
Yeah, it is done.
Okay, so
Thank you.
yeah, sure.
Okay. So Abhirup is always helpful. So here you can see that when you're learning linear algebra, you need to have very good idea on vector spaces, matrix operation, inner product norms. Now, try to understand what I'm trying to tell is that one way is that you learn linear algebra for this sake of study. Another is that you learn linear algebra, and when you learn vector spaces and inner product and norms, you now know that yes, these parts are well related to general relativity. So these are going to be very important. So here you can see diagonalization, linear transformation, symmetric and anti-symmetric of matrices, this is the electromagnetic field tensor, which is antisymmetric, the metric tensor, which is symmetric tensor. So all this actually comes from what is the linear algebra part. So these are some of the good books. This is a recent discovery, although it is a very old book, that this is a very good book, Elementary Linear Algebra. This you can go through. And the good part of this book, you see that linear algebra, I have underlined, because whenever you're reading a book, you need to be careful about this part, that it is a cohesive subject and not simply a collection of isolated definition. And you see what the author has written. Because of the smooth transition for Rn to general vector spaces is difficult for many students, yes. Considerable effort is devoted to explaining the purpose of abstraction and helping the student to visualize. Here you can see proofs are presented in a patient style, and even the people who are coming from computer science, biology, physics, business, and economics, they can learn this book. So it makes it clear, and also there are certain mathematical history which is being covered. So this gives a clear clarity what is the objective of the book and how useful it will become. This is a short content of the book. This is, I don't have to tell, this is one of the best, perhaps the most popular and one of the best books in the world, Gilbert Strang's Linear Algebra. And this is detailed content of the book, which gives you a very good confidence that yes, you can do linear algebra. This is also good linear algebra.
Yes, sir. Sir, one thing I want to say that book, Gilbert Strang, that is our textbook of statistics graduates and postgraduates also.
Yes, absolutely. So
I have read this book actually, yeah.
Yes, absolutely. No, the thing is that what I'm trying to make a point, Samrit, is that one part is that you learn linear algebra, you learn partial differential equation, you solve them. Another is that when you learn those concepts, you know that if I learn these concepts, then this part of general relativity will be clearer. So it is a reverse way. One is learning just for learning. Another is learning with an objective. And learning with an objective gives you better motivation. It gives you better clarity. So, for example, measure theory, group theory, real analysis, you keep on learning and learning and learning, doing the mathematics without any objective. Because can you see real analysis in this room, or when you go out for shopping? You cannot. But if I show you that what is the real meaning of doing the mathematics and its relation to our subject, which is general relativity, that becomes much easier.
Actually, sir, I want to add something. That is,
yes.
We cannot see mathematics. We cannot taste mathematics. The mathematical things is all about realizations. That what's going on. What is the analogy behind this fact?
Right. Yes. Absolutely.
So it's all about so how can we taste mathematics? It's all about visualizing that facts.
Okay. Absolutely. And so you have an objective that, you know, this is what is going to happen. Okay. So just before I go ahead with the last part of today's podcast, just a quick question to all the 24 candidates. Are you all enjoying, I mean to say, are you getting something to learn, or is it boring? So you can just tell me, unmuting yourself. This is a usual thing which I do in my class, that I just ask, are you all enjoying, or is it not something which is not going good? So anybody, Chandrajit, Apurva, and all others can tell me yes or no, or you can respond to me.
I think Subhash Sinha has raised.
Yes. So is it all going okay? Nice and fine with Cosmic Charade? Okay.
Yes, I think it's going very interesting, because the thing is the students should get some sort of a broader scope, not just very specific, which can happen in class anyway. Absolutely. But here what the students are getting is like a broader scope of how to do mathematics. Absolutely. What are the books possible, which would be easy, which would be a bit difficult. And this kind of this kind of a more friendly kind of discussion is always helpful.
Right.
I guess
you can find mathematics opening up any book, any blog, any website. That is not my objective. My objective is to make you aware and give you a different kind of an understanding that how, it is more of how. what you already know. You are all graduate masters in mathematics statistics, but question is how. Okay, Safal is telling is interesting and enjoying, but sadly my mic is not working. Okay, not a problem. Okay, let me quickly get back to the next part. This is also a nice book, Tom's outline, but I won't recommend to go for this book because I have read there are a lot of printing mistake in this book. Okay, so don't rely on this book. Okay, this is also fine, linear algebra and introduction. Okay, this part 2 you can go, but the mathematics of the linear algebra, etc. Okay. Now we come perhaps to the most interesting and the beautiful discussion of tensors and general relativity.
Yes, sir. One thing I want to add is that before
Yes.
going to start this discussion about linear algebra, that one should start beginning of linear algebra by the Gilbert strength, because it gives you a meaning. It gives you what should I say? Clear
It
understanding
gives
that
you an
why.
objective, actually, a
Yes.
step-by-step approach.
Yes.
Yes.
Why should we start with matrix algebra, then it going to deeper into the linear algebra?
Right.
Then
Absolutely.
definitely the done right is one of the best book, I would say. My IMS,
Right.
some of juniors suggested me that that brother, you should study these sort of books. And
Right.
definitely Indian Statistical Institute, some of the fellow suggested me go with linear algebra, Rao Bhim Shankaram. So that book is quite rigorous. Okay,
That is a very rigorous book. Yeah,
rigorous.
right.
So before going to start any kind of hardcore theoretical and rigorous study, I should say that start with the very basic and very beginning things. That what is the
Absolutely.
motive and the goal of these things.
Absolutely. And
Yes.
also, Abhirup, I would like to tell you very recently, also you should remember that always classical books are not always the best. Recently, I
Yes.
mean to say only today, I made a very detailed video on how to learn differential geometry. And you know, all the students who are there or the people who are pursuing PhD, etc., you can learn through calculus, you can learn through linear algebra, you get through geometry, but you know what you are stuck up. That is called how to understand a proof-based mathematical system, real
Definitely.
analysis
Definitely.
in one way.
Definitely.
And this is something which I see students get stuck up. I mean to say, if I give that, okay, this is a bottle and this is a mobile, how will you prove this? This is difficult.
Yes.
How to prove this is a bottle, this is a mobile. So proof-based mathematical system typically going into real analysis doesn't make any sense. First of all, use the proof in order to prove simple statements in English. If A is an integer and B is an integer, how do you prove that A is an integer? Simple English. So classical books like Gilbert Strang's is definitely good, but nowadays I'm doing a lot of research in discovering very recent new books which are also better. Okay, let me go back to this part quickly.
Yeah. Definitely.
So we go into tensors. Now you see that I have a very detailed video, a lot of videos I have made on my channel on tensor. But what I'm trying to tell is that this is actually what is a tensor. It is used in anatomy, etc. So it has something to do with stretching and pulling. So you see that on the left hand side, there is a sphere, okay? And I pull and I pull, I stretch that sphere and it becomes an oblate spheroid. So the red color, which I have underlined over in the sphere, that is a data, whatever data. Samrit deals with a lot of data. So whatever the data it is, when it goes into an oblate spheroid, it gets distorted, it gets stretched. So the question is that how can we learn about that stretching part? Remember that in case of a general relativity, we are not talking of these usual Cartesian coordinates. So it will get stretched, it will get deformed, it will get scaled, it will get shortened, etc. So whatever happened, what has Einstein told us? Einstein told that whatever happens, but the laws of the nature should be the same. Isn't it? Apurba and others, you agree to that, right? So the laws of the nature has to be the same. Now, if I have to make the laws of the nature same, but the coordinates are all changing because we have moved out from Euclidean to non-Euclidean, different types of coordinate, what is the concept? What is the mathematical tool which will help us to measure the vectors to be invariant? And in this occasion, I would like to make a note that remember, that Einstein was not aware about tensors. Okay, he knew nothing about tensors. He was totally unaware about tensor. And if you go back to my videos in General Theory of Relativity, etc., I have actually shown, and there are proofs from the history, from the pages, that one of his friend, I don't know whether you know his name, Marcel Grossman actually was a master of differential geometry. And in that, area, Marcel Grossman was actually a master. Okay, I will just give you one link in this chat box. You can go ahead and watch it. So Marcel Grossman actually taught Einstein that, hey, come on, sit by my side. I'm going to teach you what is called tensor. Because remember, tensor was discovered much, much, much earlier to Einstein. Okay, it was basically discovered, why? Because people were studying crystals, crystallography. Crystallography required tensors because crystals expand in different direction when they are heated. So Voldemar, Voigt, Ricci, there are different people who studied tensors. They discovered tensors, and that was basically done when this crystallography was done. So remember, Einstein really struggled, and it was Marcel Grossman who helped him to learn tensors, and that is why tensors came, and we got General Theory of Relativity. So here you see a nice description from flat space to curved space. If objects stretch, if the coordinate system is rotated, whatever happens, the laws of nature should be invariant, and that is what it comes at the tensors. And here you can see in Einstein's field equations, these are the capital.
Sir, one thing, your screen is not visible. Please reshare your screen.
It's not visible. Your screen is still. This, what happened? Resume.
Sorry, I shared my screen by mistake. That's when it happened, sir.
Oh, okay. Is it now visible?
Not yet. Please share again.
Sharing is already on. I mean to say, click or to resume or cancel your presentation. Is it now visible?
No.
Sir, maybe you can.
I can see the page actually.
Okay, now.
Yeah, I think it's better if you can pin that page. There should be some option of pinning that page so that it comes to the front.
Pinning that page. How will I do that? Okay, let me stop the sharing, and shall I reshare it?
Yes. Please stop. Share it.
Resume presenting. Yeah.
Now it is visible. Yes. Exactly.
Yes,
Now
sir.
it's visible. Okay.
Yeah,
Sir, can I ask a question?
Yes.
Okay, Apurva has a question. Yes, tell me.
So, sir, here you said that whatever happens, the laws of the nature should be invariant. So, what I can understand from the context of classical physics is that, like a very famous experiment of even in the times of Galileo. So we throw a ball. We throw a ball in an inertial frame, like in the ground, and we do the same experiment from a train which is moving in constant speed.
Right.
And so I understand from that context that the laws of Newton and other things should be invariant. But
here, Apurva, what is happening is that whatever you are saying, that is on a Euclidean plane, where it is basically the geometry is flat.
Yes, sir.
Here the geometry is curved.
So yeah, my question is which natural laws we are talking about here? General relativity.
We are basically talking about everything. I mean to say measurement, angle, momentum, velocity, everything which happens on a curved space. A space which is curved, because angles will no longer be, some of the angles of a triangle won't be 180 degrees. It can be 270 degrees. It can be less than 270 degrees, right? It might happen that the straight line is not a straight line, it is a curved line. Pythagoras' theorem is failing. So when we are talking about the laws of nature, that means we are talking about the measurement. How do we measure things? On a curved surface, these are not following the laws of Euclidean plane. The mathematics is not the same as what Euclid has taught us. So we need to invent a new type of a geometry, new kind of a mathematics, that whatever twist and turn you are doing, but the measurement or the measurement in terms of the angle, velocity, whatever, it should be the same. We will come to that part. I will just show you how it is. Okay. Okay. Now you see here, okay, can you see the screen right now? Is it showing an animation?
Yes. Yes, sir.
It is showing the animation.
Yeah.
Okay, good, very good. So the first R is called as the Ricci curvature tensor. I'm so sorry, I don't have the time to explain this. I wish I have already done in many of the videos. You can go ahead and check it. This is how a volume of matter changes when it moves from flat space to curved space. Answering to Apurva's question, what do we measure? For example, volume. And this volume is not ordinary volume, it is a differential volume. Okay, you will come to that. The next, this R, it talks about Ricci scalar. That means if I take a ball and if I move that ball in a Euclidean space, and if I move that ball in a curved space, how much the deviation is. Don't worry, I will show you a very quick figure. Okay, now you might ask that why it is a ball. I will come to that later, because we are talking of the earth as a sphere, so it will take spheres and balls. This G we have already seen, the metric tensor, which are the 16 components you just saw, isn't it? Reduced to the 10 components. The next one is the Riemann curvature tensor, which is hidden. It is a contraction of the Ricci and the Ricci curvature scalar, which is not there, it is hidden. It is a derivation, which unfortunately I cannot show. And this T is the stress energy momentum tensor. So just to answer Apurva's question, Apurva, you can see whatever is on the left-hand side of this equation, the left-hand side, it speaks about how to measure the curvature. And what causes the curvature? The matter, the mass, the ball, or the building, or me, whatever. And how do you measure that? That is the T, that is the stress energy momentum tensor. That means whatever stress, whatever energy, whatever a matter causes, that is reflected with this tensor T. And whatever the curvature which is happening is measured by Ricci, Riemann, metric tensor, all of those. Okay, this is another video. Okay, any question I think we have? How does the space curve? It doesn't have mass. Okay, this is a very good question. I would like to answer. The space, if it doesn't have, even if it doesn't have a mass, it will have a negligible curvature. But as Einstein's field equation deals with massive things, now, for example, I am sitting here right on the chair. This is also causing a curvature on my building's floor. But that curvature is so minimal that Einstein's field equation won't be able to detect it. So that is the thing that you need to understand. Okay. So here you can see, this is another video which you can go ahead and watch, Einstein field equation for beginners. Okay. So why tensors are unique? You see now here that on the left-hand side, there is a static frame of reference and I have rotated it. So as soon as I rotate, you see AX vector becomes bigger and A prime Y is shorter. So when Apurva, I hope that now you can understand that what are the physical changes? These are the changes. So if I rotate it, if I stretch it, how things will happen. Now you see this. Pythagoras' theorem is not going to work on a curved surface. And in order to measure the curvature, what we need is a metric tensor or a tensor. So all those things, the covariant derivative, the Ricci tensor, Ricci scalar. Now don't ask me what is a covariant derivative. I have to show again a derivation. But this is actually a generalized form of the general derivative. General derivative actually fails in the curved spacetime, so we need a covariant derivative. So all these things, what is the basic bottom line? The bottom line is that all these things helps us to measure the distances, angles, or the the entire geometry of space-time. Now you see what I was telling you. You see the first figure, the sectional curvature, the Ricci curvature is 0, because if I move the ball, it will be straight. On the left-hand side bottom, you see this is a converging geodesic. So if I move the ball, it shrinks in size. And on the last right-hand side, this is a divergence. So the ball increases in size. So the decrease, the increase, and zero change, these are basically happens when the ball moves through the sphere, the geodesic, and the curvature and everything, the Ricci, the Riemann, all those tensors actually measures this thing. I hope that can make things clear. This is a very, very old video. I remember this is perhaps my first video 2 years back on Ricci tensor, Ricci scalar, and you can look into this. It gives you a very detailed understanding, which due to lack of time, I cannot tell you. It is there on my channel. So you see here, tensors are not to make your life tense. So tensors remove tensions, right? So here you see that if I want to write the Ricci tensor 0, 0, 0, 1, 3, 3, this, it will eventually create a 4 by 4 matrix. So how do I write it? Just R mu nu. That's it. Again, T 0, 0, 0, 1, 0, 2. Again, it is written in T mu nu. So this is the way in which tensors are making your life easy. That means you are contracting a lot of things into one single equation. So you remember, I told you that this equation is a set of 16 equations. We talk it as it is an Einstein field equation, but it is wrong. I will tell you it is wrong. It is equations, because all these are equations within the bracket that you see. These are contracted and written in one single form. Okay, what are the books on tensor calculus? First, point number 1, it is one of the best books. I think it is a Bible. Everyone should read it. It is very cheap. I think even the PDF copy is available. Student's Guide to Vector and Tensor by Daniel Fleisch. And here you can see already this book contains a lot of stuff about what you call general relativity, metric tensor, Riemann curvature tensor, covariant differentiation. And it is a super, super, super book. I repeat, super, super, super book. And you can understand just reading on your own. Nothing to go, no professors to ask. Okay, this is a great book. This is also a very good book of G.E. Hayes, Vector and Tensor Analysis. It also gives you a lot of stuffs. If you want to know about the tensor calculus of physics, this is by the German writer Dwight E. Neuenschwander, and this carries a lot of good things. And remember, the good part is that this book starts with Euclidean geometry. And that is good because it first brushes you or give you a kind of a refresher course on Euclidean gradient, etc. Then it moves into theory of relativity, etc. And my favorite is Professor Prasun Kumar Naik's Tensor Calculus and Differential Geometry. This is, I think, one of the best books. So first one would be this one for a very basic understanding. Then you should go to this one for physics part, and then you should go for this. And this also carries everything. It is mathematical, as Abhirup has pointed. It is a mathematical book. So don't explain very simple explanations. Riemannian geometry, etc. is being covered. And I have talked about all those in this video. Okay. Now I will come to the final part, which is differential geometry, which is another integral part of general theory of relativity, because I will just take a pause and try to make you a point. Samrit, do I have another 10-15 minutes time quickly?
Yes. Yeah, sure.
Okay.
No problem.
So differential geometry, why it is important in general relativity? Because again, we are dealing with what we are dealing with geometry. And this geometry is not a normal geometry. This is a, I would say a geometry which would require calculus. Why it will require calculus? Because we have to deal with infinitesimal small surfaces. So here you can see, why do you need? Because differential and geometry. Differential means differentiation and geometry means geometry. But this geometry just to tell you, is not the Euclidean geometry, it is the non-Euclidean geometry. Now here you see that from flat space-time, we are moving to curved space-time. This is the transition. And general relativity is all about curved space-time. So here you see the person who was asking me that you now you see the measurements. Apurva, kind attention for you. You see the sphere. The angles are not 180 degrees. And you see this saddle surface, hyperbolic geometry, it is a negative curvature. So in order to measure, how will you do that? You use calculus. And this is basically what is done on a concept which is called manifold. Manifold, if you go to a truck driver and if you ask that what is a manifold, the truck driver will show you the toolbox. So that is also a manifold. But we are talking about a different kind of a manifold. So here you see that in Newtonian mechanics, we consider force, but in general relativity, we consider as a curvature. So more massive the object, the person who was asking, the deeper is the curvature. So what is the role of differential geometry? The role is that it will help you to know more about the curvature of space-time. So you cannot distinguish differential geometry and tensor separately. It is more or less in the same book. So how do you do that? That is differential geometry. You need differential geometry. Why? Because as you can see on the left-hand side, blue, this is the curved surface. This is the curved surface. And this curved surface has got all the motion. Apurva was asking that what is causing that. So you see the motion, the force, the electromagnetism, whatever is happening, this is happening on the curved surface. So in order to measure the curved surface, you need differential geometry. So you can see the positive, negative, and the zero curvature. How do you take a portion of it, you differentiate it, you use the rule of calculus, and you get differential geometry.
Sir, we have a question, maybe.
Sir.
Okay. Just a second. Yeah. Sir, I have a thought about the previous comment. Firstly, objects beyond the universe have like planets, Earth, and so on, which while revolving and rotation and gravity, while also spaces of some objects on the orbital property, mentioned gravity creates a bend of space around it due to high amount of energy through, but mass and energy is a proportional, speaking of that. Hence, it bends the neighborhood bit. I mean the space around. Yes, I'm going to say this is right, whatever you have told. So when it creates the kind of a curvature, that curvature is basically mentioned by, it is registered or calculated by Einstein field equations. So hence it bends the neighborhood of it, I mean the space around. Yes, mass and energies are proportional. No, here mass and energy are proportional. It means that it is not that E equal to mc squared that we are talking. That is on terms of special relativity. Here we are not talking considering the speed of light. Here things are moving in the speed of gravity. So here the curvature is caused by the mass. I hope Safal I can make things understand. Okay.
Sir,
yeah.
Sir, as we are going from Euclidean to non-Euclidean geometry, yes. So do we have to even change the very basic theorems of triangles we study in flat surfaces?
Yes, yes. That is why I showed you this one. Let me show you again once more. Oh, sorry. This one. Theorems you have to change. No, you don't have to change the theorems. The thing that who is that Chiranjit, right? What you are asking is that theorems in the Euclidean space will be there. You don't have to change it. But when you come to the curved space and you try to make an angle on a football, you will see that it won't measure 180 degrees.
Sir, we have questions. One more.
Yeah. Why do we need the curve? Why do we need to curve the space itself to create gravity? If this theory was so correct, it should have been applied to quantum theory as well. No. Why do we need to curve the space itself to create gravity? We really don't need to curve the space. The space itself is curved. If this theory was so correct, it should have been applied to quantum theory. No. What you are talking, I don't know your name. So what you are talking, are you talking about quantum gravity, where quantum mechanics and general relativity are taken together? It is not yet done. If this theory was so correct, it should have applied to quantum theory. No, why will I apply to quantum theory? Quantum theory deals with quantum particle. If you're talking of quantum field theory, that deals with special relativity and quantum mechanics. But why will I apply this to quantum theory? Because that is small and this is large. That is what I am asking. Are you talking about the quantum gravity, where all the theories merge together? That you need to tell me. Okay. So why will I use? Because quantum mechanics is quantum. This is large. Quantum theory is very successful. Quantum field theory is very successful with classical physics, special relativity, and quantum mechanics. General relativity talks about big things. Now, if you're talking about quantum gravity, that is different. Okay. Okay. Samrit, I have to rush up, I know, because this part I will quickly go over. What is a manifold? Now, who was asking? Chiranjit. Chiranjit, now you see what you were asking, the basic theorem. No, you don't have to change. If I take a space, for example, the blue one on the left-hand side, and if I use a microscope, a magnifying glass, and I zoom and zoom and zoom and zoom, it will become locally Euclidean. And that is what is the beauty of manifold. Okay, and this is what is described by differential geometry. So if a thing becomes a locally Euclidean, that means the manifold is homeomorphic. Again, we are talking very technical terms. Homeomorphic means a cup and a donut, both of them are the same. So the beauty is that, now let me explain you clearly. So if I got a mobile, this mobile, it is visible, okay, right?
Yeah.
So if I deform, I cannot break, sorry, this is my office mobile. If I deform this mobile into a bottle like this, I deform this mobile and it becomes a bottle like this, then that is what is called a manifold, okay? So I zoom this bottle, I zoom and zoom and zoom, and it becomes a flat space. It becomes locally Euclidean. That means this mobile and this bottle, they are homeomorphic. That means some characteristics of this mobile will be the same characteristics of a bottle, and that makes life easier. Why? Because when we are studying differential geometry, if this space and this space are common, then if I know the characteristic of this space, I can know the characteristic of this space also. Let me show you quickly what I'm trying to show you. Trying to mean. You see this one. So this is a box. I blow air and it becomes a larger and a larger and a larger. So this is homeomorphic. That means it is smoothly transitioning without any break. You go to my video on topology, I have shown physical demonstration with clay. So physics which is there on the left hand side will be the same around there, will be same around there. Isn't it so beautiful? So all of them will have a common feature. And if all of them have a common feature, then it is easy to understand what is going on there. I won't go into this because this would again go into topology, but this is manifold, and this is why general relativity depends on manifold. So Apurva was asking a weird surface like this. If it is the manifold of that, it is a manifold. So if I can calculate something here, it will have the same feature of that. So physics become easy. Can two space-times that are homeomorphic can have different physical properties, or does homeomorphism implies physical equivalence in the context of general relativity? No. Homeomorphic, again, it will be very local. So space-time, Abhirup, is very wide. So we cannot consider the homeomorphism of space-time. We can only consider homeomorphism of a small local neighborhood. Very intelligent question. Thanks, Abhirup, for asking this. You will get the answer to this question in today's video. Go to today's video, which I have launched. Okay, homeomorphism is something which is local neighborhood. So we cannot apply topology over there. We only apply differential geometry in a local neighborhood. Space-time you're talking is huge. Right? Okay, I will answer to this question later because Samrit is looking at the watch. I know it is getting late. Okay.
No, no, it's not late. You can continue.
Okay. Okay, fine. So what are the books on manifold? This is a very good book. Famous mathematician Loring W2 and Introduction to Smooth Manifolds, John M. Lee. This is also good. I will quickly pass over what are the books on differential geometry. First, start with curves and surfaces. This would give you a very good understanding. Then go to this book, Elementary Differential Geometry. Okay, one thing I would like to mention, whenever you're selecting a book in differential geometry, please read through the back portion of the book, because some books in differential geometry assumes that you know topology. And if they assume you know topology, you are in a mess. You are in a problem. You are frustrated. Right? What is the name of your channel? I am new here. The name of my channel is Physics for Students. I will just share the link over here so that you can go ahead and check it later. So this is my link for Kankana Banerjee. Remember, so whenever you are selecting a book on differential geometry, please do remember that are you checking that you know topology or not? This book of Andrew Priestley assumes that you don't know topology. Okay, so check it. I have given how to check it in today's video. Today's video is almost 1 hour, but it contains a lot of understanding about differential geometry. This book is also good. This book is also good. And this is my favorite, Tristram Needham's Visual Differential Geometry. And why this is my favorite, you see, the content of the book actually covers everything. Differential geometry, Riemann curvature tensor, general theory of relativity, special theory of relativity. It contains Euclidean space, what not. I mean to say, it is one book which will answer everything related to curvature, tensor, differential geometry, Einstein curvature, and you see Einstein's curved space-time, the happy thought, Schwarzschild solutions, black hole, everything. Everything. This is a very good book on differential geometry. Okay. The last topic, and I will pause. Non-Euclidean geometry also is required, because there are two types of non-Euclidean geometry, elliptic and hyperbolic. You already know this is a positive and this is a negative curvature. Why? Because you see, this is the original writing of Hermann Minkowski. I have actually done a big video on the development of space-time, the concept of space-time by Hermann Minkowski. So here you see, this is what? This is a hyperbolic geometry. And Minkowski space-time is the light cone itself is a hyperbolic geometry. So if you understand hyperbolic geometry, you can understand things better. Now this is a kind of my suggestion, that also learn elliptic geometry. Why? Because I have shown just now that elliptic geometry is positive, right? This is a positive curvature. So if you are doing a research on general relativity, and for example, you want to make a kind of a, what I would say, a theoretical model. I would say not theoretical model. It is called a assumed model, a perfect kind of a model. Okay, where everything is on a positive curvature. Suppose, for example, you're creating a model, then you can use elliptic geometry. Okay, so a kind of a ideal universe. Yes, this is the right word. Ideal universe. For example, Schwarzschild solution. So Schwarzschild metric does not happen for rotating or charged black holes. That happens only for non-rotating and spherically symmetric black hole, right? So if you want to develop a general relativity solution where everything is nice and fine, you can use elliptic geometry to do that. And this is a very good book. I would strongly suggest, please go ahead. You can find this book on the internet. This is a must book for all the students. How Euclidean geometry came into flow, and then from there, how the transition happens. See, most of you, don't take me wrong, most of you concentrate more on the mathematics, but you never try to know why mathematics evolved. Who were the people? What was the reason? So this is the development and history. That means you really come to know a lot about the history. This you won't find anywhere else except Shounak. This is a very rare book about Euclidean, non-Euclidean geometry. Part 1, Part 2, Part 3. This is also a good book, but still I would say this book is a must, because you will see how geometry has evolved. Okay, then this book of mathematical association, this is also good. These are all hyperbolic geometry, but it gives you a very thorough understanding of Euclidean geometry and then takes you to non-Euclidean geometry. So these are the pillars: partial differential equations, differential geometry, non-Euclidean geometry, linear algebra, and tensor calculus. So that's it for today's podcast, and thank you for watching. You can go ahead and subscribe to my channel, or you can talk to me. So over to Samrit. I hope that this session has created some amount of impact and you have learned. Thanks, Trillion, for Amarpal Singh. Yeah, see, this is something.
Yeah.
Sir, I have few questions.
Yes. What are those?
Sir, I have already written in the chat
Can
box.
homeomorphism be used to classify singularities or provide a clearer understanding of their nature? Singularities in the sense, which singularity? Are you talking of the mathematical singularity?
Yes.
Okay. So, so mathematical singularity is something where there is a, I would say, there is a problem. I mean to say a problem in terms. Can I stop the sharing now, right?
Yes, yes, yes. No, no issue.
Yeah, yeah, sure.
Have I stopped the sharing? Let me. Is it
Yes,
stopped?
yes, it's stopped.
So now the question, Abhirup, is that if you're talking of what is called a, you know, what it is called mathematical singularity, then I would say that is what is where there is a problem, where you're not finding the laws of physics to be right. So I still cannot understand that. So what it has to do with homeomorphism? Because okay, let me answer it in this way. If you take two singularities, okay, which are, again, we are talking about topology, I'm so sorry. So if you consider two singularities which is topologically equivalent, okay, and there exists a kind of a homeomorphism, that means this can be transferred into another, right? What does that mean? It means that from a topological point of view, they are fundamentally the same structure, if I consider two singularities. So in a broader context, Abhirup, homeomorphism can help us to understand singularities. Because if this is topologically same, why not? So in case of certain singularities, I mean to say those are, I mean to say you have to take it very simple, ideal conditions. Otherwise it will be difficult. Homeomorphism can provide a mean to classify them. Okay, if those are topologically equivalent. Also, I would say if f1, f2, these are two functions and they have singularities and these can be related to homeomorphism, it would suggest that their behavior might be, you know, a kind of a fundamental similar to that. But again, there is a limitation in terms of homeomorphism. And what is that? Again, if I go to the global structure, which I was telling. So homeomorphism deals with the overall, you know, similar continuous behavior, but not the specific details at the singular point. So homeomorphism might not be applicable or suitable for all types of singularities or functions. I hope that answers your questions. Sir, please make a bigger podcast next time. Okay, that is up to Samrit sir. So, yeah, because as I told you, some of the students might be disappointed today, because as a subject told that I cannot teach every single concept of general relativity in an hour's time, not even hour, 2 hours, not even 2 hours. I have to divide 2 hours into 10 or 12 sessions, right? And through that I will do, which I have already done in my channel. There are many videos and I'm still making videos which. But the idea what I told to Samrit, and thank to Cosmic Sharad for holding this, is that more is the how. What are the books? What are the approach? What are the do's? What are the don'ts? We might have a separate session which speaks about the evolution of general relativity, etc. Okay, happy Guru Purnima. Absolutely, sir. You are, yeah, today is Guru Purnima, right? You are doing great. Okay, Amarpal Singh. Sir, I said before that messaging, etc. That was the amount of gravity which leads to the surface of the around neighborhood, sir. So can you verify this if I said it went? I mean not necessarily proportional to c square, but in the view when mass is large and produce gravity, the larger mass is, and I cannot get you. Safal, if you can talk, I think there's a problem with the mic, or you can get to me later through WhatsApp also. I think so much to read. Yeah.
Sir,
So
Ankush, sir wants to ask something.
yes,
Yeah, so it's just a discussion about what Apurbo was questioning, that whether about the Euclidean geometry, that three angles make up 180 degree, whether these theorems has to be completely forgotten and new theorems comes up. So my modest answer would be no, because you see,
yes,
whenever we do a new theory, that new theory should be able to prove the older observations to some special limits. For example, if I take Einstein's relativity, well, Einstein's relativity is, or the special theory of relativity is also a very general concept. On the other hand, it should be able to reproduce Newton's law at the limit of low speed. Otherwise, Einstein's theory would fall flat,
absolutely,
would completely be wrong.
absolutely.
So there is no kind of fear that we have to learn general theory of relativity and then we have to completely forget what we have learned in school. No, whatever we have learned in school should come up as special cases. So it's not that there is no fear about that.
Absolutely.
A very easy example to understand, because Apurbo is actually a graduate student, as I understand, from of physics. A very easy example would be to take up quantum mechanics. And if you see the quantum mechanics as an equation, it starts with the Schrodinger equation, right? But then it builds up the Ehrenfest equation. And the Ehrenfest theorem is actually a restatement of Newton's laws of motion.
Absolutely.
You see, so that means quantum mechanics is not everything. It has to reproduce the classical physics, the classical physics at its proper limit.
Absolutely. And I would also wholeheartedly agree with what Ankush Sengupta is telling. And remember also Schrodinger equation. I don't have I was reading, there was a load shedding, today for about 3 hours. So I picked up this wonderful book, John Gribbin's Erwin Schrodinger and Quantum Revolution. So remember also another thing is that Schrodinger equation, supporting to what Ankush told, Schrodinger equation is a classical equation. Ankush, do you agree to me, right?
Yes, classical in the sense it's not relativistic. Schrodinger equation is a non-relativistic equation.
Kinetic energy and potential energy, that together makes up the Schrodinger equation. Now, in order to make it relativistic, we go to Dirac equation.
Yes. So there, Schrodinger equations won't work again. We have to take help of Dirac's equation completely. Yes. Nice point.
Absolutely, to agree with Mr. Ankush what he told, that remember Einstein's field equation and general relativity, if you take it back, exactly what Ankush told, if you take it back under low gravity, small dust particles, it will eventually go back to F equals to ma.
Yes, exactly.
Right?
Sir, one more thing here. If I take the special theory of relativity and write down the kinetic energy equation, it will be simply the total energy mc square minus the rest mass energy m0 c square, right?
Absolutely.
Now if I make a very easy kind of Taylor expansion of this with respect to v, everything will fall flat and t will come out as half mv square. So you see, Apurbo, this is the fun that we can start with a very general thing and then apply special limits to come up with those.
So Ankush has actually told a very important thing which I would like to speak for a minute, and after that we'll end. So Ankush has actually told two very important ideas for young people. The first idea is that it is very unwise and very foolish to tell that a theory is wrong. You cannot do that. Newton was wrong, okay, Galileo was wrong, and Einstein was right, and relativity was right. So Ankush has told a very important part, and this we should be clear that you cannot tell that something is wrong. What Ankush and I am both of us are trying to tell is that one theory has got a limitation, we are extending that theory. Remember, we are extending. And
Yes,
Ankush has
yes.
told that sum of the angles of a triangle is equal to 180 degree. It still holds, and it will still hold, isn't it? But in greater dimensions, in a manifold, in differential geometry, etc., these things has to be extended. New mathematics have to develop. New things have to come, tensors, etc., geodesic, etc. So nothing is wrong, and nothing is, I would say, we are not forgetting anything. Everything is right, only we are extending what Ankush rightly told, special theory of relativity. When you do a Taylor expansion, it gets back to that.
Yes,
So
yes.
this is a very important point. Yes, Apurva, your question.
Yes, yes, sir. I have understood all of this thing. Thank to Shounak sir and Ankush sir. But I have last question. So the question is, when you said that non-Euclidean geometry is divided into two parts. First is hyperbolic, and second is what you have said, spherical or something.
Elliptic.
So my question, elliptic. So my question is, can't it be any arbitrary curvature? I mean, over a sphere, we are studying the geometry.
Any curvature, whatever kind of a curvature you are doing, all these are being measured by any equation of differential geometry. Okay, you can measure any curvature, any line that you draw, arbitrary. I am telling that this is a broad category. It is not that it has to fall under that.
Okay, sir. Okay.
That overall, when we talk of non-Euclidean geometry, it is hyperbolic, elliptic. There are many other geometries, symplectic geometry, Finsler geometry, whatnot. But overall, when we talk of non-Euclidean geometry, we learn the hyperbolic and then the elliptic, and there are many other geometries. All of them are non-Euclidean, remember. Right?
Okay, sir. Understood.
Yeah. One more thing, sir, about Apurva's previous question on the Drude model. I just had a quick sort of glance through it. What Apurva was trying to say about classical and what the Drude's model say is, Apurva, you know, the Drude model, it says that it is every metal is a chassis of metallic ions, positively charged, and a gas of electrons, right? That's the main thing that what they say?
Yes, sir.
So now, while treating this electron as a gas model, I can use either a classical statistics or a quantum statistics. So in Drew's model, they use Maxwell-Boltzmann statistics, which is a very classical statistics. And that is why they are saying it's a classical model. But if I want to do a proper, accurate theory, I cannot treat electrons as classical gas particles. They are actually quantum in nature. So they should follow classical, they should follow quantum statistics like Fermi-Dirac statistics. If they are fermions, electrons are fermions. If they were bosons, then they have to find the follow the Bose-Einstein statistics. So here for the Drew's model, they actually take Maxwell-Boltzmann statistics, and that is why they are claiming it to be classical or semi-classical, not quantum. I hope that sort of ends the doubt there. Maybe.
Okay, Samrit, I have just given, with your permission, my phone number to Safal, because he's telling how can I connect later. So this
yes, no issue.
This is my number,
Yes.
and this is my email ID, contact.physicsforstudents@gmail.com, and this is my channel, youtube.com/physicsforstudents, where I am trying to do the best. Okay, Abhirup, to answer your question, this will require again a lot of time. And to be very honest, I have not studied much about quantum gravity, but how to apply topology or homeomorphism to quantum gravity, I really don't have much idea. This quantum gravity is something which is still not yet defined. The research is still going on. So the concept of homeomorphism, as far as my little knowledge goes, is in terms of topology, and topology in terms of local or global objects. Now, how this can be elaborated to quantum gravity and space foam, I really have not worked, to be very honest. So that is my limitation. I just told you on that. Okay. So
Sir.
I think, yeah.
Yeah, sir, I have already shared the that WhatsApp group link. So I will add Shuffle, or I will share the group link to Shuffle directly. and
Sure,
he
sure,
will connect you because he has
sure.
some sort of very insightful questions. What I realized, he
Yes,
couldn't express his whole idea throughout this just because of
yes, yes.
uh,
We can connect and talk later. Right,
yes,
right.
just because
Mhm.
of very problem in his
In his
mic.
mic, right, right.
Yes, but
What I
he
really enjoyed today, first of all, my heartfelt thanks to Samrit, taking his time out of his busy schedule, Abhirup, and all the 24, 21 now participants today, is that you have really patiently listened for almost a 1.5 hour podcast. And I remember this year I did only one general relativity webinar, and that was through Google Meet. It generally goes to 2.5 hours. And my wife keeps on telling that, come on, it is dinner time. So you need to finish it by 10:30. So I made it a point that I start by 7:30 and 7:45. And Samrit has told me, sir, you need to log in by 7:45. So because general relativity is so huge, and I actually specialize, when I started my channel, Abhirup was the only member. And you are just like my family. And I feel that during that time, I was making videos over a sketch pen and a white paper.
yes, yes. Actually, sir, I know you since 2017 from the Facebook page of Stephen Hawking. You run.
Facebook page of Stephen Hawking.
Yes,
Yeah.
when I
So,
have just started my journey of math physics, actually
right,
I was in the door of higher mathematics and
right.
physics. Okay,
I
so
always see Abhirup Mitra has got a like or a comment in each of the videos. So, and, and today when I make videos on quantum field theory, quantum mechanics, linear algebra, etc., I know that my audience is primarily on general relativity. So whenever there
yes,
is a video on general relativity is coming up, Abhirup will be there and all the subscribers will be there. But I felt that Cosmic Charade has done a really wonderful job arranging this podcast and connecting you all, because after all, we are all the same. We are all striving to learn more about mathematics and physics. The group which is there, which is quite, I would say, active, and I also keep on posting new things. 28th of July, this is next Sunday. Abhirup, you might be knowing,
yes,
Professor Rajesh Kumble from ISER Kolkata
yes,
will be
yes,
coming
yes,
on my channel to speak about black holes and general relativity. So anybody can join, and I keep
definitely.
on, asking. Next month, there's a surprise. I'm trying to get a big shot person from string theory to come up.
Mm-hmm.
A great pleasure. Again, million of thanks to Cosmic Charade Group. And those who do not know Cosmic Charade and Samrit and Abhirup, please do support them, because no, not Brian Green. Kankana is telling Brian Green. No. Brian Green won't listen to me. But I have tried to contact somebody in string theory. Okay. Brian Green, I dream. I used to tell to my wife early in the morning, I saw a dream, and my wife asked me, what was the dream? And I told, my dream was there was a load shedding, and there was a podcast going on with Sir Roger Penrose. And there was suddenly a load
Uh,
shedding, and for 5 minutes, the podcast was lost. So, there is no harm in dreaming high, and Cosmic Charade is also dreaming high. You've got a very good programming group, art programming, and I'm very jealous about Abhirup Maitra's all written, T-shirt. I told that, where have you got? I also want that T-shirt. So, I always dream that, maybe one day Brian Green or Leonard Susskind, we would be able to speak. So let us keep on dreaming high, because I never thought that Professor Shayantan Chaudhary, Sudesh Nadi from this Fermi lab, she came on particle physics. Then another great person called Professor Soumitra Sengupta, very known person, everybody knows, from Indian Association of Cultivation of Science. He came, but I keep on dreaming high. And anyway, so 10:05, it's dinner time. Samrit, thank you very much for all those.
Mhm.
Thank you very much.
Yeah,
And
Thank
yeah,
you.
we are
Thanks a
going to
lot of
end.
for your wonderful
Yes,
talk.
yes,
thank you. Good.
yes, well, thank you, everyone. A huge thank you to our special guest, Mr.
No,
Shounak
I'm no
Bhattacharya.
special. I'm absolutely ordinary.
No, you are special to us.
Another number, sir.
And to our amazing team, Obhirup, Sandipan, Kaji, Snigdha, and Rajat, your hard work and passion towards this cosmic charade, and which makes this postcard shine brighter
And
than
we
any
would
star
also
in the
like to
Milky Way
meet
galaxy.
someday. Let us make an event, like we can meet over a cup of coffee, etc. Don't worry, the bill will be on me. I'm okay with that. But we can meet someday, and physical meeting is required. I always tell Abhiru, last year also I told that why don't you arrange a meeting when people are coming to Calcutta? I am also not in my tour, etc. Let us meet one day, because it will create a huge amount of difference. Virtual is okay, but let's meet one day. That would create a lot of
Sure.
Definitely, we
right?
can.
Definitely.
We'll
As
try
I tell
to
that a lot of
organize
things
an
can,
in-person meetup.
We are.
Yeah, a lot of things can happen over a cup of coffee.
Yes, sure.
Yes. Yeah, we are working on this actually to make it happen soon. So yeah, let's see.
Amarpal
And
Singh,
yeah,
great.
thank to our listeners. And thank to our listeners also being part of our cosmic community. Keep looking up those stars and wondering, because that's where the magic happens. And until next time, stay curious, keep exploring, and remember one thing: this universe is full of
And I will tell you the
waiting
last
to be uncovered.
I will tell you the last secret and suspense. I pinged Obhirup at, I think, 5 o'clock. And you know why I pinged it? Because there was 3-hour load shedding going on. I told Obhirup, I don't know what is going to happen. Till 6 o'clock, there is no power. And the moment I said hello, the power came in.
Yeah, I have seen a hello in my WhatsApp text. Yeah.
Yes, and that was a negative hello, because I was supposed to tell that Obhirup, I don't know, I will wait till 7:30 and 8, and when we are starting. And the moment I told hello, the power came in, and I sat with my final presentation.
Yeah, that's really cool. Okay, thank you so much, everyone.
Thank you very much.
Let's good night.
So, Samrit, you will put it up in YouTube at Cosmic Sharad's channel, right? Everybody can see that.
Yes.
Okay,
This whole session is recorded, and it will be available in the YouTube channel.
Okay. Goodbye. Take care. Bye bye. Have a nice day.
Goodbye.
Bye.
Goodbye.
Thanks a lot.
Yes.